Hello, today we're going to talk about calculating the equilibrium constant. The next slide we're going to have a short refresher from section 3 on how to write expressions for reaction quotients or equilibrium constants. And then we will get into how do we calculate the value of the equilibrium constant. So if you have more complicated reactions, you're going to have a more complicated equilibrium constant or reaction quotient. So in order to figure that out, we need to use what's called an equilibrium expression or a reaction quotient expression. It's the expression there, and it depends on whether you're doing concentrations, which should be in molarity, or if you have pressures, which will be in ATM. Now, concentrations, that's why you see QC or KC. Again, molarities, and you'll need to use brackets in your expression. Brackets always indicate molarity. And then pressures, you'll see QP or KP, and you want to use the partial pressure notation there. So when I write PC, that means the pressure of substance C, the partial pressure of substance C. And we'll put that in parentheses. We don't use brackets because brackets indicate molarity. Now, once you kind of figure out whether you're doing concentration or pressure, then you're going to follow this kind of pattern here. If there's a coefficient in your balanced equation, the coefficient becomes the exponent. All right, coefficients become exponents, and it's always products over reactants. One more little rule is that you never include solid substances or liquid substances. They do not affect the value of your equilibrium constant or your value of the reaction quotient. They're still there and they're still necessary for the reaction to happen. So you have to have like some of it present, but the specific amount of it does not affect the position of equilibrium. Alrighty, so now that we have that little refresher on how we write equilibrium expressions, let's go ahead and do an example where we calculate the value. And so we have this reaction between copper 2 plus ions and lead 2 plus ions to form copper 1 plus ions and lead 4 plus ions. And they give us these values for an experiment. They don't tell us that it's at equilibrium, so they want us to find the value of the reaction quotient. So we need to write the QC expression. It's in concentration and it's not at equilibrium necessarily. So we need to put the products over the reactants. We have the Cu1 plus ions squared because of the coefficient, the lead 4 plus ions, the copper 2 plus ions squared because of the coefficient, and the lead 2 plus ions. Now that we have our expression, all we need to do is plug in the numbers into that expression. So we want to put the copper 1 plus is 2 molar squared, the lead 4 plus is 3 molar, the copper 2 plus ions are 4 molar squared, and the lead 2 plus ions is 5 molar. And I just kind of abbreviated, but you should use the 3 sig figs in your answer. I abbreviated to make it shorter in the expression itself. And so you just need to plug that in. 2 squared times 3 divided by 4 squared times 5. And when you plug all of that in, you get 0.150. And there's no unit for Q or K. There's no unit because it's just a ratio of amounts of products to reactants. So there's your value. So here's another example. They give us that Kp is 0.061 at 500 Kelvin, and they give us the partial pressure of N2, 2.34 atm, H2 is 4.56 atm. What is the partial pressure of NH3? So this time we're doing Kp, it's equilibrium. We want to first always write our equilibrium expression, and we want to do the products over the reactants, pressure of NH3 squared over the pressure of N2 times the pressure of H2 cubed. And now we can start plugging in our values. They gave us Kp is 0.061. We don't know the pressure of NH3. N2 is 2.34, and H2 is 4.56 cubed. So make sure you're paying attention to those exponents. And then from here, all you need to do is solve for the pressure of NH3. Solve the bottom of your denominator, multiply both sides, and then take the square root. And you get that the pressure of NH3 is equal to 3.68 atm. Okay, here's another one. We want to find the reaction quotient, QP. These are in pressures. So we have the pressure of CO2 cubed times the pressure of H2O to the fourth, all over the pressure of the C3H8 times the pressure of the O2 to the fifth. And then you plug in your values for QP. The CO2 is 0.789 cubed, and then the water is 0.123 to the fourth. C3H8 is 1.23, and the O2 is 4.56, and that one's to the fifth. And then you just plug it in, solve for QP. 4.64 times 10 to the negative 8. Don't be alarmed if you have very large numbers or very small numbers. It's totally possible when you have equilibrium amounts, because it's just a ratio of the amounts of products to reactants. If you have way more products, it's going to be a very large number. If you have way more reactants, it's going to be a very small number. All right, last example, we have an equilibrium expression for case C. We want to always write products over reactants. So C squared times D all over A squared times B. And then they gave us the equilibrium values. They tell us equilibrium constant is 0.0234. And then they tell us that C is what we're looking for. D is 2.91. A is 0.261 squared, and then B is 4.13. So then you just need to solve for the value of C. And we get that C is 0.0476 molar. That's our molar concentration when we solve for C.